Section 5.5 of your text deals with how you can use mathematical induction to prove some statements dealing with algorithms and how you can prove that algorithms are actually correct. It is not officially part of our class, but it is something those of you who are going to go on to work in computer science and take an algorithms class will have to work with in an algorithms class. Just a suggestion, you may want to keep this particular textbook because it will be a help to you in seeing how to deal with algorithms being correct, and there are sections on how to classify algorithms called Big O and Big Omega, and you might find that the way this textbook describes it is in keeping with what you've learned here, so it may help you when you do this in an algorithms class. Section 5.6 and 5.7 deal with recursion, and the way they approach it in your text is they will look at a bunch of different problems, and in section 5.6 they look at how to approach the problem recursively, and in section 5.7 they'll take a look at how to find an explicit formula for that problem. I'm going to do something just a little bit different here. We're going to take a look at 5.6, and in this video we're going to talk about the basics of recursion. We'll do some examples from your text in the next video, and then we're going to take a look at the problems of the Tower of Hanoi, compound interest, and the Fibonacci sequence, and we'll look at both the recursive formula and the explicit formula for many of them, and do it together that way. And then at the very end we will take a look at arithmetic and geometric sequences and see how they fit in with this. See that we can have an explicit formula and a recursive formula for each of those. Well, beginning our discussion of recursion, let's look at the definition of recursion that you have in section 5.6 in the blue box in your text. What it says is that a recurrence relation for a sequence, and here's a sequence we have, it's a formula that relates each one of the terms in the sequence to one or more of its predecessors. So it's going to look at the ones before a sub k, like a sub k minus 1, a sub k minus 2, and so on, where I is an integer and k is any integer greater than or equal to I. That sounds a little familiar, and it should, because it sort of fits in with the way we were doing things with strong induction. The initial conditions, sometimes called the seeds in computer science, for such a recurrence relation specify the values of these, and while mathematicians may start these at a sub 0, computer science people always start them, some mathematicians may start these at a sub 1, but computer people always start these at a sub 0, because that matches up with the way we number things in an array. One of the things you do in computers is you often define functions. We're going to be doing a whole section in functions in this class. But one way that a function could be defined is using recursive format. Here is a function. It happens to be done in C, but it's a simple enough function that I think no matter which languages you're familiar with, whether it's Java or whatever, you should be able to read this particular one. And this function does something that we're used to working with. This function shows the way we find n factorial. Remember, n factorial is found by taking n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. Well, the recursive function is done sort of the back way. It says we'll start here with an initial condition where it's 1, and then we can do the 2, then we can do the 3, and so on. What it says is when we pass an integer n to this, is if n is less than or equal to 1, the reason we have the less than or equal to 1 is so that it'll handle the special case of 0, or if you happen to accidentally pass this thing a negative number, it's just going to return 1. So if n is 1, you notice 1 factorial is 1, which we've done before. When we go beyond 1, look what it does. It returns 2 times 1 factorial. This function calls itself. This function is calling itself this way. And so this one gives us 2 times 1, or 2. When n is 3, you see we're doing 3 times 2 factorial, which is calling itself, and then it's doing 3 times 2 times 1 to get 6, and so on. We've seen that before in our definition, but here it's defined in a recursive format, and it's often done in computer science because you'll see that there are some things you can only define recursively. There are some things that we can define recursively, and then we can simplify them by making an explicit formula. There are 2 examples that are discussed in section 5.6 and section 5.7 that are very common examples, and we'll analyze these in detail. One of them is what's called a Fibonacci sequence. The Fibonacci sequence goes like this. 1, 1, those are our seeds, and then for the next one, we're going to take 1 plus 1 and get 2. 1 plus 2 and get 3. 2 plus 3 and get 5. 5, 6, 7, 8, and so on. So we're always adding the 2 previous terms to get the next one. Fibonacci is kind of the nickname or pen name for a mathematician called Leonardo of Pisa, and he described this in terms of rabbits reproducing. The numbers here represented the pairs of rabbits, and you can read through the problem a little bit, and basically it says what happens is you start out with 1 pair of rabbits, but they can't reproduce during the first month, so you still have only 1 pair. But then the next month, that pair produces another pair, and you still have the same original pair of rabbits. Well, the interesting thing here is, of course, one of the assumptions about this is that the rabbits never die. So you see the first month you have 1 pair, the second month you have 1 pair, the third month you have 2 pairs. The next month, the same thing happens over here, and you have those rabbits reproduce. This particular pair hasn't been around long enough to start reproducing, so now you have 3 pairs. The next month this pair is still around. This pair has not been around long enough to reproduce. This pair has got another one. This pair is still around, and this pair reproduces. So you have 2 pairs that are reproducing. So you see here what we have is 2 plus 3 giving us 5, and this pattern continues. The interesting thing about this pattern is it happens many places in nature. The Fibonacci numbers appear in biological settings, such as the branches on a tree. Now, I know there's 2 pictures on the PowerPoint, and I've included the PowerPoint slides on Blackboard, but I'm going to draw a little different picture here. If you look at certain kinds of plants, you may see that the branches come up and split up in different ways like this. And what you see is a row with 1, another row with 1, then a row with 2, then there's some row where there's 3, and then on another row you'll get 5. These 5 little leaves on here. So you can have branching that works like this. This pattern also happens with the way the sprouts appear in a pineapple, the flowering of an artichoke, an uncurling fern, And if you pick up a pine cone, you'll notice this pattern in the way all the little nuggets are in the pine cone. These applications also pop up many places in computers. They're used in computer algorithms such as the Fibonacci search technique, Fibonacci data structure. There's a simple recursion of Fibonacci numbers that's inspired a family of recursive graphs called Fibonacci cubes for interconnecting parallel and distributed systems. I've recently been working with a software development technique called agile programming. And one of the things you have to do is you assign a task size to every job that you're doing. And the task sizes that you use, and sometimes we actually use little playing cards that have these numbers on them, are going to be the sizes that go 1, 2, 3, 5, 8, going along in a Fibonacci sequence. We're going to deal more with the mathematics of a Fibonacci application in one of the following videos. Also in one of the following videos, we're going to take a look at a problem called the Tower of Hanoi, which has got an interesting little story about this tower in a great temple. And it talks about having, and you may have seen little kits like this, something set up with 3 pins on it and a group of discs, and you move the discs from one to the other. I suggest that you read over section 5.6 and 5.7 before you play the videos on how to work with the Fibonacci sequence and how to do the Tower of Hanoi, and we're going to analyze those in there. The next video is actually going to show how we can use a predefined recursive formula to see patterns.